Hello, this is Jack Jackson again. We're going to be talking about phase shift identities today. So when we get our Cartesian coordinate graphs of the sine and cosine waves from, starting with unit circle, and then when we produce these graphs, the Cartesian graphs we notice are waves. And we really notice that it looks like these graphs are really the same shape, just shifted over from each other. So they have a horizontal shift or phase shift from one to the other. And I think you can see by looking at this that the smallest amount of the shift that we could do would be if we take the sine wave and then shift it to the left by pi over 2. So we notice that in general when we have this, I've got this graph set up so I can move this yellow point, and it traces along an x value on the x-axis here, and then it goes up and finds the cosine of that, up or down, and finds the cosine of that as the y value on the blue curve. Then it also finds a point that is pi over 2 to the right of that, okay, and that is a point on the x-axis, and then I find its y-coordinate on the sine graph, and we notice that those are the same, and that's the same anywhere we go. Also notice that as I move this around, you can see the corresponding picture down here in the unit circle picture, and this point, let's just watch the green point down here. It corresponds to the yellow point up here in the graph, and notice as I go in the positive direction, that's going to spin around the circle in the positive direction. Whereas if I move to the left up here on the graph with my yellow point, I'm going to be rotating in the counterclockwise or negative direction. Okay, so it does look like that this is going to work out for us, and it turns out these two blue links here and here are the same as the blue links here and here, and so we see that those are the same. Now, so we remember in general that if we graph anything, relation in x and y, and then we change the x to x plus pi over 2, that we really shift that graph to the left by pi over 2. So if we graph y equals sine of x plus pi over 2, that should be the same as the graph of y equals sine of x, but shifted to the left by pi over 2. So if I graph this, look what happens. Notice that it is right on top of the cosine graph. So in fact, these really are phase shifts, and so we can see it that way. Now that's basically what all this text down here is saying. Okay? Now, if we want to actually prove this formally, then we need to be looking at the unit circle picture, and we can do it this way. So here's the proof, and we'll break it down in all possible cases. And so as we're doing this, we're going to move the yellow point around for each of the different cases. So the first case is when it's on the x-axis for the terminal side. So that would be like here at 0 or at pi, any multiple pi, or 2 pi, or 3 pi, any integer multiple of pi, we're going to end up on the x-axis. And when we do that, we notice that the two blue links are 1, and that's a typo, let's fix that. And so the cosine of that angle is 1, and the sine of pi plus t, well, where's pi plus t? Well, if you're on the positive part of the x-axis, it ends up here on the positive part of the y-axis. Let's see, actually let me rephrase this. If it's on the y-axis here, then the other point is on the x-axis, and they're both 0. Okay, so let's illustrate that first. So let's put it first on the y-axis. So that would be at odd multiples of pi over 2. That would be like here. And so that would be at pi, over 2, or 3 pi over 2 would be here. Okay, and notice in both of those cases, when it's on the y-axis, the other one is on the is ahead of it by a right angle, ahead of it by pi over 2. So it's going to be on the x-axis, and in both cases the sine of the one here and the cosine of the sine of the one that's on the x-axis is 0, and the cosine of the one that's on the y-axis is also 0. So those are both 0. Now let's look at what happens next if you're on the if it is on the at the point 1, 0. So that would happen like when the t is 0, or at 2 pi, or 4 pi, and so forth. If this point here is at 1, 0, then this point up here that's pi over 2 ahead of it is going to be at 0, 1, and we see the sine of the one up here on the y-axis is 1, and the cosine of the one down here is 1. So they're both the same. Okay, I'm just checking for typos. That looks like that's correct as well. Okay, so now if we have, let's look at the next case. The next case is when we're here. So the terminal side is over here on the negative part of the x-axis, so the point cosine t, sine t is at negative 1, 0. When that happens, then this is going to be pi over 2 ahead of it, so it's going to be pointing straight down, and it's going to go through the point negative 0, negative 1, and so the sine of this point down here is negative 1, and this cosine of this one over here is negative 1, and so those are both the same. So now we've showed that this identity is true no matter where we are if we're on an axial angle. Well, what if we're in a first quadrant angle, like right in here? Whether it's in here or over here, for the x doesn't really matter, but let's say we're in here. Now look at what happens. When you're pi over 2 ahead, that makes a right angle right here on the unit circle diagram. Okay? And then notice that our reference angle right here, compared to the reference angle right here, they have to be complementary angles, because these three angles add up to a straight angle, pi, the measure of a straight angle, so that would be pi. And so that leaves these two to add up to pi over 2, so they're complementary angles. Well, that makes the angle up here, well, these two angles in here are complementary as well, so the angle up here is congruent to this one. This angle here is congruent to that one. And so by angle, side angle, or angle, angle, side, because the side we know is the hypotenuse. Okay, so either by angle, side angle, or angle, angle, side, we get these two triangles are congruent, and the way they correspond is the two blue sides are congruent there. Well, the blue side is down here is basically the cosine of this angle that goes the green terminal side, and the blue side here is the sine of this one here, and notice that those are going to be the same size. Okay, however, what about the signs, positive or negative? Well, we notice that both of these are positive, that the cosine in the first quadrant and the sine in the second quadrant are both positive, so in fact those are actually equal to each other. Okay, now what happens if we go over to get the original angle t to have terminal side in the second quadrant? Well, this time our two reference angles again are complementary, but this time because they add up to a right angle that you can see right there. Okay, they're actually adjacent, and their outsides make up a right angle. So they're certainly complementary there. Again, for similar reasons that we got before, these two triangles are congruent, again with the flip. So we see that the horizontal distance here for the green terminal side is the same as the vertical distance for the other one. So we know that the absolute values are going to be the same. So what about the sines? Well, the cosine of this point, of this terminal side here, that angle in the second quadrant, is going to be negative, and the sine of this one down in the third quadrant are both going to be negative. Okay, so if we're in the second quadrant, then they're both negative, but they are equal to each other. All right, so we're getting still our theorem, our identity seems to be true. So let's go over here and put the angle now in the green angle in the third quadrant, terminal side in the third quadrant. That means the terminal side of the purple one is the purple terminal side there is going to be in the it's pi over 2 ahead, so it's going to be in the fourth quadrant. Okay, and again, those two triangles are congruent, again, kind of for the same reason. We get our reference angles here and here are, again, complementary. They, along with the right angle, all three add up to pi, so the two smaller ones add up to pi. Again, for similar reasons as before, we're going to get those two triangles are congruent with the two blue sides congruent. The blue side over here is going to be the cosine of this one, and the blue side here is going to be the sine here, except notice that they're both going to be negative values, but again, that makes them equal, so again, we get that. Finally, one more case is when the terminal side of the green original angle T is in the fourth quadrant. Then we see this picture, and again, our reference angles are congruent, and our reference angles are going to be in the, they sum up to a right angle. This time they're adjacent again, so you can see that they're clearly, well, the reference angles are not congruent, but they are complementary, but there's a congruent angle up here. So the two marked angles here are congruent. And so that gets us to congruent triangles, and it also gets us the two blue links here, and this one's hard to see that it's blue, but underneath that it's blue. There it is. And those two links there are the same, and so again, this blue vertical length is the sine of the angle T plus pi over 2, and the horizontal length, can't tell it's blue, but it's from here to here, is the cosine of this green one here, so that's cosine of t. And again, they're both positive in this case, and so they are the same size exactly. So in all three cases, we were able to get that is proved. Little black squares sometimes put at the end of a proof to say, okay, we're done, we proved what we set out to prove. And so we were able to prove it formally by using the unit circle picture. We can see it visually probably better by just looking at the graphs, and we see that when we shift the red graph to the left by pi over 2, we get the blue graph. So shifting sine to the left gives us cosine, and so our identity is that sine of x plus pi over 2 equals cosine of x. Now, because of this, we get a very similar relationship between secant and cosecant, since they're just reciprocals of sine and cosine respectively. So we get a similar proof that cosecant of t plus pi over 2 is equal to secant of t, and the proof is very simple here once we prove the other one, because cosecant of t plus pi over 2 by the reciprocal identity is 1 over sine of t plus pi over 2. By the identity we just proved, sine of t plus pi over 2 is cosine of t, and then 1 over cosine t is secant of t, and that proves our proof. Again, we use the reciprocal identity twice, two reciprocal identities, and then the phase shift identity that we just proved. And so that means when I graph these, we should, just as we saw it in the sine and cosine, the secant and cosecant are going to shift. The brown one is the secant of y equals secant of x, and the purple one is y equals, the brown one is the y equals cosecant of x. It's the reciprocal of sine of x, and the purple one is y equals secant of x, the reciprocal of cosine of x. And so we see that those are reciprocals of each other, they're phase shifts of each other, just since they're reciprocals of the sine and cosine. And so again, we see that if we take the brown graph of cosecant and shift it to the left by pi over 2, we get purple graph of secant.